Was about where we left off. We were talking about binary search. So if I said find a number, if it exists in this collection, now here are all the numbers between 1 and 15, okay? Now obviously, if you look at this and you're like, that's all the numbers between 1 and 15, and if I ask, does it include 7, you go, obviously. But remember, you don't really know, okay? We don't know what's in this data. So if I wanted to find a number, I would do something like this. I'd start, well, is it 8? If it's not, because I know the data is sorted, because it's sorted, I know if the number I'm looking for is more than 8, it must be on that side, right? If it's less, it must be on this side. But no matter what, if it's on that side, I don't need to look at anything over here anymore. It's done. And I've eliminated about half of the stuff from my search. Let's say I'm looking for the number like 11, right? Is it here? No, but it's less, so it must be over here. Well, is it 10? No, it must be there. We find it. Now, this was one of the worst case scenarios in a binary search. Worst case being like I make all possible guesses, right? There's no number to the right of 11 because, well, that would have been 12, but 12 was like up there, right? And if you're wondering, how did I do that? Well, I picked 8, and I went like halfway between 8, like 1 and 8, 4, and then to the 12, and so on and so on and so on, okay? So that's how it's broken down. But that's a worst case scenario. But consider the fact that the worst case scenario is only 4 guesses, right? At most, I have to make 4 guesses. I have to look at 4 numbers to find what I'm looking for, at most. Where in the linear search, do I have an example of that? No. In the linear search, at most I have to make 15. Four is better, right? If I'm looking for the number 8 and I go like, all right, 8. Oh, I found it. I got it in 1. Fine, I got lucky. That would be like looking at the beginning of the list and finding what I'm looking for. So why not always do a search like this? It's clearly better. Well, why not? Well, the data must be ordered for this to work. I have to be able to say, like, is it 8? Or is 8 the thing I'm looking for? No? Well, should it go that way or that way? I have to be able to know which way to look. If this data is not sorted, I have no way to know, right? I don't know if the data to the right is actually bigger than the thing I'm looking for. If that was the case, I can't use this type of search. Yeah. So, anyways, there is a relationship between the maximum number of checks that you'd have to do based on the size of the haystack. The relationship is that n being the number of guesses you make is going to be related to 2 to the power of the height of the tree plus 1 minus 1. Ugh. There's a lot going on there, but we would just be like, there's a relationship between n and 2 to the h. Because again, we're lazy about those. Like that's the relationship. As the height grows, the number of nodes grows. As the number of nodes grows, that's how the relationship between n and h. Really, that's what we're showing. It's a loose relationship that we care. So as n grows, the maximum number of steps that could be taken grows, like log base 2 of n. Now, you might think like, hold on, when we just looked at Fibonacci and it grew like that tree, and that was exponential. How come this is logarithmic? We're going to talk about this in more detail, but it makes perfect sense because it depends on like what we're looking at here. Right? The number of nodes, if I know what h is, if I increase h, the number of nodes grows like 2 to the power of h. If I increase the number of nodes, the height grows like that. It's the relationship between the number of nodes and the height, right? We'll see it in more detail later. Basically, if I have like right? this is the height, and the number of nodes is the number of nodes. Okay? If I add one more to the height, how embarrassing. If I add one more to the height, I like double the number of things in this tree. Okay? 8 plus 4 plus 2 plus 1. So 8, 9, 10, 11, 12, 13, 14, 15. And then I would have 16 things down here. I like more than double, right? But you could also say, like, I would have to double the number of nodes before I really add like a whole new layer. So it's how we relate these numbers together. The n versus h. That's what we're getting at here. One grows really big as you increase that. The other one grows really small as you increase that. But they're just the inverse of each other. It's all about the direction. So how would I do a binary search iteratively? Okay, well, here's how we do it. Now, mind this whole t extends comparable nonsense. This means that this method, or this static method, would only work if the type t that we have in there is comparable, that there is some ordering for it. If they can't be ordered, I can't do a binary search. Iterative binary search, we have needle and haystack. How do we do it? Well, it's really not too bad. It might look complicated, and it's definitely not trivial, but it's really not too bad. Right? I start with low index. Imagine I've got some array with n things in it. Or let's say n minus 1, and whatever, who cares? I start with low index, high index, and the middle, which is going to be about like n over 2, right? Which is the high minus low divided by 2. So n minus 0 divided by 2 in this case, right? You see? And then I check. Okay, well, the low index is less than the high index. Well, that's true. If haystack.midpoint compared to needle is 0, we found it. If you remember, compared to when it returns a 0, it means they're equal. And if I found something I'm equal to, I found the thing I'm looking for. Great, we return the midpoint. I found it. Otherwise, if, now this might be weird. Yeah, okay, I'll come back to that in a second. Objects compare the midpoint and needle. If it's greater than, that means the thing in the haystack is bigger. That means the needle must be less than that. The needle must be over here. So what do? I set the high point to be midpoint minus 1. Why minus 1? Well, I just checked if this was the thing I'm looking for. So obviously midpoint isn't it. So I update this such that this is now low. This is now the high point. Okay? And the midpoint is now here. And then I would repeat that again. Maybe this becomes low and then the midpoint. And then this becomes high and that becomes the low, and so on. And we can narrow down until we find it. And if we ever get to the point where the low and mid, or the low and the high become not that case, low less than, if they ever become equal, it must not be there. How could that happen? Well, imagine like low, imagine a very simple case where, let's say we have 0, like we've gotten down to a very small list. 0, high is 2, and mid is 1. Oops. Right? And let's say the element just isn't there, right? But if it did exist, maybe it would be between 0 and 1. I don't know. Okay? I would say midpoint becomes 1. Or midpoint is 1, so the high index becomes 1 minus 1. Now it's clearly not there, right? If it's not here, but it should be between, it must, there we go. I guess I say, well, it's not less than. Well, low is less than the high. Yeah, anyways, cool. Cool? That's the idea, iteratively. Not found, there we go. This code really isn't too bad. Hopefully we see how it just systematically updates what the low and the high are, calculate the mid, find out where it goes, updates the low and the high accordingly. Cool? Cool. Now, what's going on here? This allows us to say, how do we compare these things? Okay? We use the t's compare to. Okay? So remember how we want null safe things? Yeah? So this would be like a null safe version, but you need to tell it which function to do it. Well, the type t's compare to is how we do it. It's kind of like you're passing a function, kind of. Yeah. Don't worry too much. It's the magic Java code. That's all. Why I didn't use it here, I can't quite remember. There's probably a reason, but I can't quite remember. Point being, this is how much, like, it's the magic code to make Java happy, whatever. I can't quite remember. Yeah, why did I not do objects compare there? I'll look into that. I can't quite remember offhand, but it's not overly important right now, okay? All right, so there, that's the iterative one. Not too bad, right? Hopefully it's not too bad. I maintain my point that it's definitely not trivial. You shouldn't look at this and understand it immediately. But it's definitely something that you should find manageable. So what's happening? Okay, yeah, we already explained it. So what would it look like recursively? Well, it looks like this. Now, with the verboseness of the function calls and the methods and whatnot, it might look kind of complex, but let's take a moment and really think about what this function is doing recursively. This function, again, it must be okay, they must be comparable. It takes a needle, a haystack, and a low and a low and a high point. If low is greater than or equal to high, it's not found. We return this not found thing, whatever, it's not there. Otherwise, we find the midpoint. We do the comparison. If it's the same, we found it. It's index midpoint. Great, found it. If it's greater than 0, meaning that this is bigger, needle must be to the left of the midpoint. And if it is, you repeat the recursive binary search. You repeat the binary search with needle, haystack, low is still low, but the high is now midpoint minus 1. So it's basically, it's the same algorithm, but it's written recursively. And again, I think because like the verboseness of the Java, this looks similarly complex, but really I think like the logic is a little cleaner. We have a low, we have a high, we calculate the midpoint. I'm asking the function, is it here basically? If it's not, just one sec. If it's not, well, should it be here or here? If it's here, repeat the same thing, but here. Find the midpoint. And we repeat the same thing by calling the recursive function, not by iterating with the loop. So first I check, okay, is it not there? I do that condition check. If we ever get the case where greater than or equal to high, it's just not there, okay. If we find it, good. If not, we'll search over here or search over there. You had a question?
Yeah, is the only major change that you put the low and high points in there as a parameter?
It's not the only, I mean, and the fact that I made it recursive, right? But that is like a big change, right? Now they're in there, right? They are parameters, and I would have to give them as arguments. Now, look at this code, though, and what is the computational complexity of this? It's not a trick question, but I definitely can see how people might make a mistake. So my advice is slow down and think about it, okay? The question we always ask when doing the analysis is, how many times, like, what is the computational complexity? Like, how many times will this code run for each How many times will this code run depending on like the input size, right? Like that's the question we're getting at here, right? Just, I'll give everyone a moment to think about it. So, I mean, this is kind of a dirty question to ask right now because we didn't talk about the computation complexity of the iterative one. And in the iterative one, like you might be tempted, like, okay, there's a loop, but it's not like a for loop like before where we knew it was going to run some number of times. So yeah, we go to the, how many times will this run based on n? Well, it turns out that this is logarithmic. Why? Well, because it will never run n times, I know that. Why? Because every time we are like taking chunks off. And how much are we taking? Well, we're not subtracting by 1, we're dividing by 2. Dividing by 2, divide by 2, divide by 2. Every time we do this loop, we divide how many we have left to look at by 2. So if you ever see like a +1 in a loop many times, think like multiplication, right? If I do +1 10 times, that's just times 10, right? But if you ever see something, oh, and similar like -1, well, that's like dividing kind of, right? But if you ever do like multiplication many times, that's like to the power of, right? Repeatedly multiplying something, that's like an exponent, that's a power. If you see repeated dividing, that's log. But what are we dividing by? Well, that'll be like the base. So log base 2, y base 2, well, because we're dividing by 2 every time. We're eliminating about half the things every time. You might say, well, we're eliminating more than half because like I look at the midpoint and I also get to eliminate the midpoint and the other half. Yeah, well, remember, we're not that precise. So it's log base 2, which is really good. Yeah.
When we're trying to figure out the computational complexity, do we state that it's log base 2 of n, or do we just say that's log n?
You usually, if you were to say log base 2 of n, you'd be correct. If you were to say log of n, you'd be correct. Because almost always in your general world, like if I'm a mathematician and I write log and I don't specify the base, it's assumed to be 10. In the context of like computer science, if you see log, it's assumed to be 2. It's often to only write the base if it's not 2, right? Even if if it was log 10, you should probably put the 10 because the computer scientist is going to assume it's 2. Sometimes the context you might be able to infer from it, but it's always good to be as explicit as possible. So saying log base 2 is always nice, but it wouldn't be weird to see just log. So I would say like O log n. Sometimes like that. You might see that. Whatever. It's all good enough. Okay? Cool. Now what about this one, right? Because, well, it's like the same algorithm, but we kind of got tricked before with Fibonacci, right? How it was actually way worse. So, I'm tempted to say it's log base 2, but I don't want to get tricked, especially because I do see there's 2 recursive calls here, right? But unlike Fibonacci, with Fibonacci, for every call, you would make 2 more calls. Here, that's not happening. If you're looking at this and you say, but there's 2 calls, these are mutually exclusive. Only one of these 2 can ever run. So, and it also still follows that these values, we're still taking chunks off of the remaining data still. So this still is log base 2. Now, obviously, this was not a particularly rigorous analysis, but I'm just trying to give you a feel for how to think about this stuff. Cool? Cool. All right. Any last questions? By the way, I will take a moment to let you know I am very happy with all of you. I think you guys are a phenomenal 162 class. So I'd like you to keep up the good work. You've been doing a really good job. I've been teaching this class for a long time, and I know that this year there was a big drop-off, and maybe that's why you're all so good. The only people that are left are those that kind of want to be here, right? Which is usually a good thing, right? But like it's this cliche, like how teaching first year is the most difficult type of teaching there is. And I've been doing it for a while. But you group, you're making me not feel horrible about myself. So keep up the good work, right? Yeah. I joked earlier with the second years too. Maybe you're not even very good. I don't know, but you're better than last year at least. So there you go. Right? Yeah. Don't tell last year I said that though. All right.
Wait, wouldn't the second year's ones be the...
Yeah, I know. I made the same joke to them. I know. I'm not that original. Anyways, cool. Any questions before we move on to trees? Who here started assignment 4? Who here finished assignment 4? Who here is shockingly far along in assignment 4? All right, nobody. This is, I guess, means nobody still. All right. All right, trees are non-linear data structures. What I mean by that is, like, a queue is linear. Why? Well, there's a beginning and an end, assuming they exist, right? A stack, linear. A list, a bag, the ones we did, they're all linear, right? If I give you a bag, and I'm going to represent it like this, like A, B, C, right? And I say A, what comes after A? You go B, obviously, right? It's linear. I can draw a line. It's linear. Now a tree is different because I can't really draw a line. And by the way, when I say like draw a line, like I mean like there's an orderedness. Now the elements themselves in this particular case are sorted. They don't need to be sorted. Maybe I should do like happy face, tree, that face, and sunshine. I've got these elements in my bag, right? There's no intrinsic ordering to them. It doesn't matter. It's not a sorted bag. It's just some index bag with some data in it, whatever. And I'm like, okay, what comes after this? Tree. And you knew that the thing that came after the happy face was a tree, not because of like how I drew it. Now, obviously, I drew it in a way that like makes sense, but like, why is it there? Well, in and of itself, the thing, like there's a successor that comes after this, right? But like if I draw a tree and I say, what comes after root directory of C drive? If this is like representing some file system hierarchy. If I say, what comes after root directory? You might be like, well, okay, it's documents and settings. But you only said that because of how this was drawn, right? Where here, you could be like, well, you drew it that, well, I drew it that way because I put the successor right there. But really, should this be before? I could have put that there. It didn't really matter. We're over here. If I drew happy face, that face, well, that doesn't make sense because it's mismatching the order. Point being, there's no like obvious ordering here. I can't draw a line connecting these things. I'd have to like lift my pencil up, right? I'd be like, okay, from here to here to here, what comes up? I don't know. Like, it doesn't really make sense. So let's define a tree. You can look at this picture and probably figure it out. Oh, and by the way, I always hated, in any class ever, whether it was high school, university, wherever it was, you always are, every once in a while, you're faced with those like lectures or new topics where it's like, let's start talking about definitions. And you're like, great, I got to memorize all this crap. Don't worry. Computer scientists are with you. And our words are pretty self-explanatory that there's really no memorizing that needs to take place here, okay? We might be weird and call that a tree, and you think like, well, feels upside down, I know. But that's really the worst of it. It's the sure. But that's the root.
Yeah, this is the beginning of the root.
Ah, okay. So a tree is a collection of elements such that it is empty, or it has a special element called the root, from which descends 0 or more trees, often referred to as subtrees. Now you might look at this and be like, oh, that's a recursive definition. Absolutely it is. This is a recursive definition of a tree. It's either empty, hey look, there's a tree, right? Or there's a special element from which descend some number of trees. Whatever they look like, who cares? But there might be trees here. And of which there might be a root node, or maybe it's empty, but from which there may or may not some other number, and so on and so on and so on. So this is a recursive definition. If we were to look at this tree, we have a root, and all of the things that descend from the root are subtrees. Now, technically, every subtree that doesn't exist here is also a tree, because it's an empty tree is a tree, which is weird, but we're not going to get into that. So a node is an entity within a tree. An edge connects them. This is probably the weirdest definition you'll have to think of. We call these lines edges. Okay? That's probably the weirdest one. The root node is a special element that is the origin of the tree, and a tree can have 1 or 0 root nodes. An empty tree doesn't have a root. Okay? By the way, you can go find different definitions of trees if you want. This is the one we're sticking with. A leaf node is a node that has no child nodes. An interior node, and when I say child node, a descendant, any descendants. An interior node is not a leaf node. And an empty tree is a tree with no nodes or edges. This is still a tree based on the definition of the tree we discussed above. Think empty stack, bag, or queue, right? You can have a queue with nothing in it. It's still a queue. Yeah?
So would the empty tree still have a root, or would it not have?
It doesn't have a root. It's empty. In the same way that like you can have a stack, and you're like, well, what's the top? It's empty. There isn't one. But it's still a stack. It's just there's nothing there. So like I said, it's possible to find alternative definitions of trees. You can go find Wikipedia, and you might find a variety of different definitions. This is the one that we're going to use. It's pretty common. You can find some really weird definitions that, and you might say, why have a different definition of a tree? Well, first of all, these things aren't like, we define them however we want. But sometimes people come up with a way to define it that has some like little quirks to it that they might want to try to take advantage of. So like it might make implementing a certain thing better if you think of a tree like this. We're not going to worry about that right now. We're sticking with this. That's just to say, why would you want a different one? Because maybe you do. So going back to this, we've got a root, we've got some interior nodes, and we have some leaf nodes. The root is, in and of itself, an interior node if it doesn't, if it does have children. But the root might also be like a leaf because it might not have children, right? That could be the case. Because this could be there, we got a tree right there. That's a tree. It's not empty. It's got a root followed by descendants that are trees. And all of the trees that descend from this are non-existent. It's a tree. Now, you might be looking at this and be like, how would you know the difference between this and like a linear structure? Well, you wouldn't based on what I have here. It's just that in the context of talking about a tree, this could have children, but it doesn't, right? So it's still a tree. All right, relationship. So we have like relative things that we can talk about here. We have a parent or predecessor of a given node is the one that comes before it. Each node can have at most one predecessor. All nodes have one predecessor except the root. The root has no predecessor. And each node could have a child or successor node, and it could have 0 to many of them. Depending on the definition of a tree, we might have like restrictions on that, but we could have 0 to many children. So when you look at like a tree, do I have an example? Yeah, I'll go to that in a second. A sibling, by the way, like a sibling is like, okay, these are siblings, right? They all have the same parent. An ancestor is anything above, and a descendant is anything below. Okay? Should be fairly straightforward based on the words we use in English. Right? Notice here, like I want you to look at this picture right here and be like, oh yeah, okay, clearly every node can have at most one parent. Again, they all have one parent except the root, which doesn't have any. But they can have many descendants. Cool? Cool? Cool. Observations, a leaf node cannot have any children. That's just like the definition of a leaf node. The root node of the whole tree has no parents. With the exception of the root node, each node has exactly one parent. A subtree of a given node is a child node and all its descendants. So like this right here, this is a subtree, right? But the subtree is not only the root of that subtree, but all the descendants in there, okay? So like, this is the child of the root, but this child is the root of some subtree. This is the root of this one's left subtree. This one's left subtree, well, it doesn't exist. It's still a tree, though, oh, right? It's just empty, there's nothing there. It's a tree. You see? That's the recursiveness there. Yeah, so subtrees of the node labeled E. See? Cool. Yeah, happy, sad, whatever. A path is a sequence of nodes and edges leading from one node to another. The path length is the number of edges, or like the number of steps it takes, not counting the first step. The level of a given node is the number of edges between the root and the node. The recursive definition is the level of the root is 0, the level of a node is that is not the root is the level of its parent plus 1. Yeah?
So the difference between the path length and the level is that the path length doesn't have to start at the node, or the root?
Well, the path doesn't need to start, yeah. So here, if I wanted to know, like, what is the path from that one to that one? Well, okay, What is the path length? Well, you can count the edges, 1, 2, 3 edges, or you can count the steps. Now, the reason I say count the edges is because, I don't know about you, how many times have you been playing like a game or implementing something and you're like, what's the length from here to here? And you're left going like, ooh, do I count this one? You know what I mean? Do I count like the 0th step, right? So if I say edges, that would be the same as not counting the 0th step. So 1, 2, 3. 1, 2, 3. That's all, right? So if you don't like counting edges, that's fine. You can count the nodes. Just make sure not to count the source node. Cool? Cool, cool. Now to get to your point of the level, it's like the path length, but from which node to that, right? So if I've got like this one, what level is this at? Well, that's 0, okay. 1, 2, 3. 0, 1, 2, 3. That's all. All nodes on the same level are not necessarily siblings, though. They could be. Maybe they're like ex-cousins, 7 billionth removed, who cares, whatever. But like, see, they're not siblings, right? But they're on the same level. Yeah?
Do those black squares, if nodes hold data?
Typically.
Do those black ones still hold data?
So here, yes. The only reason they're black is for like the visual clarity from before, about like the ones that were black were leaf nodes, right? They just don't have any children. So this one, this here is, we haven't talked about like a tree as a data structure. We're just talking about it as some construct right now. We'll get to that, I think. But to give you a little sneak peek, yeah, this has data and some number of children. Data, some number of children. Now this one has data, but no children. Yeah. You can find definitions of trees where you represent, and I don't like this one, where you represent like empty trees as a node that exists with a special value, like a sentinel value or something, right? So maybe I could have drawn like bright red boxes like here, but they would mean like there's nothing there. But in my opinion, if there's nothing there, there's nothing there. Just get rid of it. Yeah. Observation, the path length between the height of the tree. The height of this tree. Did I mention height? Yes, I didn't. The height of a tree is the number of levels in the tree. There you go. Or the maximum path length from root to
Which
something.
is different than the number of levels, because there's 4 levels here, but the height's only 3.
Ooh.
Right?
The height of an empty tree is 0.
Which it should be.
So it's not the number of levels. You're right, it's not the number of levels because you count the 0th one. That's a funny little thing you caught there.
Okay. Yeah, when you were showing the log function earlier, it was like, it's weird.
So to be clear on his point, he raises a good point, is I'm talking about like,
I guess at that point, it's like, is the ceiling a floor?
sure, but it is a good point.
Yeah.
The height of a tree is the number of levels. How many levels does this have? Right? Well, 1, 2, 3, 4. There's 4 levels, but this is like the 0th level, right? It's kind of that 0. That's kind of a funny little thing. Yeah, that's funny. Good point. No one ever caught that before. So the height of an empty tree, the height of this tree is 3, and you're like, what? No, it should be 4. Well, 0, 1, 2, 3. So really, it's like the height of the last level, whatever. Yeah, I'll figure out how to reword that.
The height of the tallest subtree.
Yeah, I don't know. Anyways, a tree with only a root has a height of 0, and a tree of an empty tree has a height of -1, which is interesting. But that's how we make the definitions work. So deal with it. So here's showing an example of numbering the levels. The degree, or like arity, degree is often the word used. The degree of a given node is the number of children it has, not number of edges, children. Okay? The degree of the whole tree is the maximum of the nodes. Okay? So I look at this tree and I go, this is like a degree 3 tree. Why? Well, this says 0 children, 1 children, 0, 2, 0, 0, 1, 3. 3 is the biggest. There you go, it's 3, right? Here, what's the degree here? This one would be 4. Why? Because, the root has 4 children. The node with the highest degree is by no means always the root, to be clear, even though those 2 examples it was. All right? There. Now you know everything you need to know about trees. Any questions about that? What was the hardest definition to learn? Edge, maybe? Edge? Yeah. I guess height because of the ambiguity. Yeah. Yeah. A binary tree is a 2-degree tree or a ternary tree. It's a general tree. Okay, a general tree is one where each node can have any number of children. An n-array tree is one where they have no more than n children. So a binary tree is one here. It's got a special name. 2, each node can have at most 2 children. And we like these. So here's the definition of a binary tree. And here's a picture of a binary tree. A binary tree is one where each node has no more than 2 children. It's a ternary tree, a tree with a degree arity of 2, whatever. If a node has children, we give them special names. Binary trees often have an orderness to them. Okay? We'll call them left and right. Right? left and right. Maybe orderness isn't really the right word, but like, yeah, I guess orderness isn't the right word, but like, they're labeled in a way where, okay, the left and the right. Okay? Yeah.
Can each node have less than 2 triggers?
Yep.
Like one?
Absolutely. Like leaf nodes exist. So, yeah.
I think more like 1, but yeah, it also seems true.
Yep. They can have no more than 2. Yeah, okay. If a node has children, they are referred to as left and right, which is also, use the context. If I were like, the left child, well, that's that one. But I could also say like the left subtree. Well, that would be like this one and all its descendants that may or may not exist. So I might say the left child or the left subtree, you know. In the above example, B is the left subtree and C is the right. Although you might say like, well, B is the left child. B is a node, not a whole tree. Well, fine, it's the root of the whole left subtree. You see? Yeah? Cool. Based on this information, what would like a unary tree be? You're yeah, exactly. Any linked, any of the linear structures where like, oh, it's got one child. Oh, one successor. Okay, great, easy peasy. Yeah, exactly. That's what it would be. Now, by the way, I know like looking at this, you're immediately thinking link structure, but we don't have to have this in a link structure, right? Just to be clear, we're going to, but we don't have to, by the way. Traversal. So with a 1-degree tree like we have right here, a simple linear structure, the order in which nodes are traversed is pretty obvious. It's pretty natural. You start at the beginning, and then you go to the next one, then you go to the next one, then you go to the next one until you run out. That's it. Obviously, there's edge cases of like, well, what if there's only one thing? What if there's nothing in there? Fine. But in general, you go here, and then I say, what's next? You go here, what's next? You go here, what's next? And so on. We could go and define other traversals. We could do that. I can make a reverse traversal, right? Okay, fine, we could do that. I could say I want the traversal to go from here to here to here to here, right? Now, okay, maybe. It's a little atypical, a little unusual. You could do it though. But the point is, there's a rather natural traversal. But with a tree, like what is the order of the, like let's say this tree, each labeled node is like its data. And I were to say, print out the data in this tree. Well, what should the order be? Well, I don't know. You know, like to me, like I would say like, okay, A, B, D, H, maybe it should go E then A. I don't know. It's not that obvious. There might be an obvious ordering, but there might be another similarly obvious ordering. My point is, it's not that there isn't orderings, it's that if I say, what's the ordering? You go, ooh, there's really not one, right? Maybe it should be like A, B, C, D, E, F, G, I don't know. So what are the, like what is the traversal for this thing? So with a nonlinear data structure like a binary tree, the order to traverse the nodes is not immediately obvious like it is with a linear link structure. Or a linear structure, it doesn't have to be linked, pardon me. But there are a few common popular options to choose from. Pre-order, in-order, post-order, level order. We're going to talk about these 4. Now, jumping ahead a moment, you might remember though that in Java, this is a Java thing, not a tree thing, a Java thing. When we make a collection iterable, we have to have it return an iterator. So ultimately, you as the programmer, I could write iterator, pre-order, in-order, post-order, level order, define the orders to iterate over this collection all I want. But I got to pick one that is going to be the iterator. Okay, I can implement them all, call them like iterate pre-order, iterate in order, iterate post-order, iterate level order, which we will see, but ultimately I have to pick one. Which one? Depends. There's no right answer. You have to pick one of 4. Why? Which one do you pick? Pick the one that makes the most sense for what you're doing. If there isn't one, flip a coin multiple times. All right.
Or just simply say not my problem and make it an abstract class.
Make it abstract and then just return unimplemented. Yeah. Okay, a pre-order traversal. So a pre-order traversal is one of the common traversals for a binary tree. The general idea is you start at the root, you get the data from that node, then you go to the right child and you do a pre-order traversal. And then once you're done that on the right child, you go to the left child and do a pre-order traversal on the left child. You may have noticed this is recursive. In fact, this is like the idea. If the node exists, access the node, get the data, do whatever we want, print it out, I don't care. Then do a pre-order traversal on the left. What's a pre-order traversal? All of this. Then do it on the right, and then we're done. Looking at this, I would say, okay, A, and then repeat the same thing on the left. B, repeat the same thing on the left. D, repeat the same thing on the left.
Oh no.
Doesn't exist. Repeat the same thing on the right. H, we're done. Repeat the same thing on the right. Oh wait, I actually skipped a step. We're at H.
You did, yeah.
Nothing, nothing. E, nothing, nothing. Nothing, 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 nothing. Done. Hey, obviously, right? Makes perfect sense. So it would look something like, oh, I already have it here. So the root of the subtrees is accessed before, pre any recursive calls, right? Pre-order is you get the data, left, right. There you go. So what would the order be? I've got it right here. A, B, D, H, E, C, F, I, G. Done. In order. This one is interesting. You go to the left, you finish the whole left subtree, then you access that data, then you go to the right. So here, I don't start with A. I say, before I print out A, do the whole left subtree. Before I print out B, do the whole left subtree. Before I print out D, do the whole left subtree. There's nothing there. D. Nothing there. H. B. E. A. I. F. C. G. Done. Here, I make the recursive call in between. The pre, we did the accessing pre. In, we did it here. Who wants to take a wild guess where the post order would go? After. See what I mean when I said we're pretty good with our words in computer science because I don't want to think too hard? Pre, in, post. So what would that one look like? We do the left, then the right, then the thing. So H, D, E, B, I, F, G, C, A. That's how it would go. And we'll end there. Hopefully you all have a wonderful weekend.